topic of this video is shear stress in bending. Just like before, we are having a beam which we are bending, but the bending of beam does not only cause tensile and compressive stress on the surfaces of the beam, but it also causes shear within the material. The best way to show how this happens is to imagine that you have a stack of wooden beam planks and they have been stacked on each other. And when we bend that stack of wood, what happens is that the wood ends, they want to serrate like this. When we have these wood beams glued together, instead what happens is that within the layers of the wood, we will be having shear stress trying to shear those plates, those planks apart from each other. This shear stress is something that we can quite simply calculate, and the following slides are going to show you an example how we can calculate that one. So let's imagine that we have a cross section shaped like here in picture. The lower section of that cross section down here, this section here, that wants to shear off, and we want to calculate what is the shear stress at that section, at that cross section, at that layer of that material. The formula how we can calculate that one is shown in here. Tau, which is the symbol for shear stress, as a function of s, which is the distance from the neutral axis, as a function of z, which is the distance from neutral axis to the point where we want to do the calculation. In this formula, the Iy is the familiar second moment of inertia in bending. V in the equation is shear force caused by the external loading. Bz is the width of the profile at the location of shear, at the location where we want to calculate the shear stress. And then finally, the Sz is the area which is shearing off, multiplied by the distance from neutral axis of shearometric area to the geometric center of the entire profile. Okay, so that is the definition. Let's take a look at a very simple basic example. So we have here a rectangular profile and it's loaded with shear force in bending. The shear force is 50 kilonewtons, and we need to calculate what is the value for shear stress within the planes in this profile. All right, we are going to calculate the shear stress in 3 different locations. We're going to calculate it at 4 different locations. We're going to calculate it at the top surface at z minus 40. We're going to calculate z minus 20, z0 and z20. So first thing we need to do is to calculate the second moment of inertia around y-axis. It's the familiar equation which we know. B is the width, h is the height, and that is power to 3, and that is what we get. So the second moment of inertia of this profile is 170.6 10 to power 4 millimeters power to 4. At the top of the profile, there is no area, so area is 0, and when we calculate the shear at the top of the profile, the shear stress actually gets value of 0 megapascals. So at the top of the profile, at the very top surface or at the very bottom surface of the profile, there is no shear stress. But when we want to calculate the shear stress at location minus 20, so 20 millimeters from the neutral axis, we can actually now start calculating the shear stress. So the area that we want to calculate shearing off area is 20 millimeters by 40 millimeters. So S at minus 20 is 40 millimeters, it's the width, by 20, so this is the area this here. That's area. And then here, that is the distance from neutral axis of the entire profile to the neutral axis of the area that is going to shear off. So that is 30. So S at minus 20 is 24 times 10 to power 3 millimeters power 3. Then, now when we have calculated that one, we can calculate what is the shear stress at location minus 20. What we get is the shear force, which was 50 kilonewtons. It is here, multiplied by the S minus 20. It is here. And then we divide it by second moment of inertia in bending multiplied by 40 millimeters. And what we get is 17.6 megapascals. The 40 millimeters is the width of the profile at the shear location in here. Okay. Then we can do the same calculation at the middle of the profile. We do the same steps. So we first calculate the S0. It is, in this case, the area is 40 millimeters by 40 millimeters. The distance from neutral axis to the center of the shearing area is 20. So we get 32 times 10 to power 3 millimeters power 3. And then the shear stress value will be 23.4. And similarly, we can calculate it towards the bottom here. In here, we see an example that we use as the shearing area. We use this highlighted area, but you would get exactly the same results if you would calculate that this bottom area is the one that shears off. All right. And now finally, we can draw the profile of shear stress. So at the top and at the bottom of the profile it is 0. At the center of a symmetric profile, only for symmetric profiles, at the center we reach the maximum value, and the profile is parabolic as shown here in the picture. So that's how we can simply calculate the shear stress caused by bending. In the upcoming videos, we'll be calculating some simple examples of this one.